In this work, we introduce Uni-SLAM, an uncertainty-aware neural implicit SLAM framework designed for real-time dense indoor scene reconstruction. First, let's provide an overview of the proposed approach. The input to our system consists of RGBD images. By leveraging an efficient scene representation, our method simultaneously performs tracking and mapping, enabling real-time reconstruction. The final output of our model is a high-quality reconstructed 3D mesh of the scene. However, neural implicit SLAM still faces several common challenges, such as noisy input data, insufficient scene representation, slow convergence speed, lack of an effective keyframe selection strategy. To address these challenges, we propose the following solutions. A novel predictive uncertainty formulation. This approach enables dynamic reweighting of loss functions during tracking and mapping, ensuring that only reliable data contributes to the optimization process. Parallel hash grids for geometry and appearance representation. Strategic bundle adjustment, which balances global and local information to enhance keyframe management. Next, I will introduce our pipeline step by step. Our SLAM pipeline consists of the two fundamental processes, tracking and mapping. The input to our system is a sequence of RGBD images. In the scene representation stage, we use multi-resolution hash grids to encode geometry, with a geometry decoder outputting the sign distance function, SDF. In parallel, an appearance hash grid branch represents scene color. This parallel representation ensures a clean separation of geometry and appearance, enhancing storage efficiency. Through volumetric rendering, we can estimate the SDF, depth, and RGB. However, not all information is equally useful for the tracking and mapping processes. To address this, we introduce an effective uncertainty estimation method, allowing us to reweight the loss function, ensuring that unreliable data has a lower impact on the optimization process. In the tracking process, the camera pose is estimated based on scene information. At this stage, only the camera pose is updated, while the scene representation remains unchanged. During mapping, both the map and camera pose are updated. A global bundle adjustment is performed every K frames to update the map. However, different camera motion patterns introduce challenges. For example, sequences from a stationary camera and a fast-moving camera provide different levels of information gain between consecutive frames. To address these challenges, we introduce an additional mapping process based on uncertainty estimation, which actively triggers local bundle adjustment to capture valuable local information more effectively. Furthermore, we propose a co-visibility check-based local loop closure, leveraging visual overlap to enhance scene consistency. We introduce the accumulated termination probability as the sum of all point weights along the ray. Based on this, we define the predictive uncertainty, denoted as beta m, which serves as a measure of uncertainty across the sampled points. Let's take an example shown in Figure A, where ray 1 hits a valid depth at point A, while ray 2 hits an invalid depth at point B. Figures B and C show the density of sampled points along these rays. In Figure D, the accumulated termination probability for ray 2 with invalid depth is notably lower. As seen in Figure E, high uncertainty regions are mainly around invalid depth areas. Finally, this uncertainty affects rendering quality, as shown in Figure F. Many existing methods lack effective keyframe management strategies. For example, Uni-SLAM and NeRF-SLAM use local bundle adjustment, optimizing recent keyframes for local consistency. Co-SLAM applies global bundle adjustment, optimizing all keyframes for global consistency. However, these methods rely on a fixed interval strategy, selecting a keyframe every K frames. This rigid approach can cause information loss, as it overlooks varying information gain between frames. Let's consider an example to illustrate the keyframe selection issue. As the camera moves steadily from frame I-2 to frame I-1 and reaches frame I, but sudden large motion occurs at frame I+1. In such cases, the assumption of uniform motion becomes inaccurate, making standard optimization insufficient. To handle this, Additional optimization steps and an adaptive mapping process are required to effectively capture the scene changes and ensure accurate reconstruction. We utilize image-level predictive uncertainty to dynamically trigger local bundle adjustment, ensuring that optimization efforts improve overall accuracy. Overall, we propose three kinds of strategic bundle adjustment, balancing both global and local information while using a limited number of sampled rays. Global bundle adjustment, local bundle adjustment, and local loop closure optimization. For more details, please refer to our paper and supplementary materials. Here we can clearly compare the differences in rendered color and depth uncertainty between the cases with and without uncertainty estimation. Next, we present some quantitative results. We achieve better reconstruction and tracking while maintaining high efficiency. Then we present some qualitative results. Our method demonstrates the ability to capture finer details, such as thin structures like chair legs, which are often challenging for existing approaches. On realistic dataset, our method can also achieve better rendering quality and captures more structural details compared to existing approaches. Thank you for your watching.